We completed the two-compartment pharmacokinetic model for the tumor clearance data. R squared of 0.99, elimination rate 0.14 per hour, central compartment volume 3.2 liters. Optimizer converged cleanly.
I understood maybe 40% of that sentence, but it sounded extremely good.
0.99 R squared. That is fundable. I am drafting the licensing agreement right now. The rate constants are proprietary. We call the platform Tumor OS. We charge per patient per simulation. Series A closes Friday.
It is mildly curious that the parameters have been estimated to 4 decimal places from 5 data points.
The parameters are not identifiable?
Patar, the optimizer, converged. The residuals are within noise. The fit is excellent.
The fit is excellent. The parameters are fiction. 4 free parameters, 5 data points. The system is under-constrained. Many parameter combinations produce the same curve. Your optimizer found one of them.
When you say fiction,
I mean, the optimizer found one answer from infinitely many.
Hold on. The curve is exactly right, but the numbers inside it are wrong. You could replace the rate constants with completely different values, and the model still fits.
Yes. There is a surface in parameter space, not a point, a surface, where every combination produces the same observable output. The optimizer stopped at one location on that surface and declared victory.
That is incredible. The model is simultaneously correct and completely uninformative about mechanism. I want to map the entire surface. Can you enumerate every valid parameter combination?
You can. It is called a profile likelihood. It would show you exactly how unconstrained each parameter is.
Tumor OS is on hold.
It is mildly instructive that licensing parameters was considered after fitting, but before identifiability analysis. This order is common.
Differential equations are how biological systems change over time. To understand why fitting them does not automatically give you interpretable parameters, we need to understand what a differential equation is actually specifying, and what it needs to be uniquely determined. A differential equation is a speed camera, not a map. It records how fast something is changing at every moment, not where the car is, not where it is going, just the rate. To know where you end up, you accumulate the rates over time. You integrate. You also need to know where the car started. That is the initial condition. Miss that, or set the camera calibration wrong, and you reconstruct a completely different road. If you have ever reported ODE parameter estimates without a profile likelihood or an identifiability analysis, subscribe. There is more to cover. A differential equation relates a quantity to its own rate of change. The simplest case, dx over dt equals r times x. The population grows at a rate proportional to its current size. Parameter r is the specific growth rate. Formally, a first-order ordinary differential equation specifies di over dt as a function of y and t. The solution y of t is a function, not a number. It describes the system state at every point in time.
When you write the equation, you already know the answer? Like you can just solve it and you're done?
Sometimes. Exponential growth has a closed-form solution. X of t equals x 0 times e to the power rt. The logistic equation has one too. Most coupled biological systems do not. You solve them numerically.
What does numerically mean?
The solver steps forward in time. At each step, it evaluates the rate equation and accumulates the result. Runge-Kutta, Euler, L-Soda. The solver controls the step size to keep the error below a tolerance you set. The output is a table of values, system state at each time step, that converges to the exact solution as the step shrinks. This is not a weakness of the method. It is the method.
What happens if the system has processes operating on wildly different time scales? A signaling cascade where some reactions are microseconds and some are hours.
Stiffness. The solver's adaptive step control shrinks to track the fast time scale. A simulation of 12 hours of biology can take 2 hours of compute time. The solution is still correct. The runtime is the warning.
Is it fixable?
Use a stiff solver. L-Soda detects stiffness and switches method automatically. If your Python simulation should finish in seconds and is taking minutes, check your timescales. In biology, differential equations model systems that change continuously. Population dynamics, pharmacokinetics, signaling cascades, epidemics. Lotka-Volterra predator-prey is two coupled ODEs. Michaelis-Menten kinetics are an approximation that arise from a more complete ODE system. SAR epidemics is 3 equations and 2 parameters.
The SIR model became famously difficult to parameterize from early epidemic data. Infection rate and recovery rate are partially confounded in the early exponential phase when you only observe total case counts.
That is a structural identifiability problem. It is in the equations, not in the data.
So the SIR model is also broken.
The SIR model is not broken. It predicts correctly. The parameter estimates are not independently interpretable without additional experimental constraints on one of them. The trajectory is right. The mechanism is ambiguous. A correctly parameterized ODE fit produces a trajectory that matches data at every measured time point, with residuals that look like noise, small, symmetric, structureless. The parameters carry physical units. An elimination rate is inverse time. A growth rate is inverse time. If your parameter is dimensionless and you did not deliberately write a dimensionless formulation, that is a question worth answering. A non-identifiable fit looks identical. The residuals are small. The optimizer converged. The parameter estimates are printed to 4 significant figures. The parameters are meaningless. You cannot check identifiability by looking at the fit. The fit will not tell you.
How do you actually check it?
2 approaches. Structural identifiability is checked analytically. You examine whether the output equations can, in principle, be inverted to recover unique parameter values. This is done symbolically, before fitting. Practical identifiability is checked numerically. You compute a profile likelihood for each parameter and look for a well-defined minimum. A flat profile means the data cannot constrain that parameter regardless of how much more data you collect.
It is mildly concerning that most ODE fitting workflows in published biology papers show the trajectory, report the parameter table, and stop there.
That observation is correct. First, gotcha. More data points do not fix structural non-identifiability. If the parameters enter the model in a non-separable form, additional observations of the same variable do not resolve this. You need different experiments. Measuring the same output more times is not the same as measuring a different observable.
Different meaning what?
Pulse chase experiments. Isotope labeling to track individual compartments. Perturbing one parameter experimentally while holding others fixed. Measuring an internal state that was previously unobserved. The experiment must separate the parameters the equations cannot separate. Second, gotcha. The confidence intervals printed by most ODE fitting software are marginal. They report uncertainty in each parameter separately. The parameters are correlated. If the elimination rate increases, the distribution volume compensates. The joint distribution is an ellipse in parameter space, not a box. Reporting marginal intervals as if they were independent misrepresents the uncertainty.
Can you visualize the full correlation structure?
You can plot pairwise scatter plots of the profile likelihood surface, or compute the Fisher information matrix and invert it for the parameter covariance. Most software does not do this by default. You have to ask. Third, gotcha. Initial conditions are parameters. If you fit the initial conditions from the data rather than measuring them directly, you have added free parameters. Each estimated initial condition is a degree of freedom consumed. In a two-compartment model, where you do not know the starting concentration in the peripheral compartment, you have added a 5th free parameter you probably did not count.
You would need to measure the drug in both compartments at time 0.
Or constrain the peripheral compartment initial condition to 0 and justify that assumption. The assumption is often biologically correct at baseline. It must be stated explicitly, not assumed silently. Fourth, gotcha. A model can predict correctly on a validation set, even when the parameters are not identifiable. Predicting the trajectory and identifying the mechanism are different problems. You validated that the model predicts the observed output. You have not validated that the parameters describe the biology.
That distinction matters when you try to generalize to a different patient population.
When a different population has a different distribution volume, the prediction fails. Not because the model structure is wrong, but because the parameter you reported to 4 decimal places was not constrained by the data you collected. The parameter was one choice from a surface of choices. Pharmacokinetic parameters from non-identifiable fits appear in the literature as biological constants. Other groups use them. Dosing regimens are designed from them. Drug interaction predictions are based on them. The original data constrained a trajectory. It did not constrain the mechanism. The distinction matters when the population changes.
Structural identifiability analysis takes less time than the parameter estimation itself. The tools exist: Strike, GenSSI, DAISY, symbolic packages that check identifiability analytically. The analysis is not routinely done because it is not required for publication.
So TumorOS is not dead. We run identifiability analysis, redesign the experiment to separate the parameters, get real estimates, and then license them.
That is the correct sequence?
It is mildly optimistic as a timeline for Friday.
I want to intentionally build the most non-identifiable ODE model possible. Maximum parameters, minimum data, see how confident looking the output is. I think the result would be useful as a demonstration.
That experiment has been done. A 5-parameter model fitted to 2 data points produces R² of 1.0. The parameters mean nothing. The fit is perfect. It would serve as a demonstration. The equation described the biology. The parameters described one version